Thanks for joining us. I know there's a lot of different cool options. Hopefully you'll get a ton out of this. My name is Kevin, and I've been working on gRPC for about 3.5 years now, and currently I'm on the steering committee for gRPC. So today we've got 5 speakers, a bunch of different people who are, on the project and maintainers in various roles, various languages. And then we have one of the folks from Broadcom, and who's a big user of gRPC. He collaborates with the team quite a bit. So again, I'm Kevin, and before I jump into things, just want to thank everybody for coming, and hope you enjoy this talk and the rest of your time here in Atlanta. One of the really cool things, that we keep an eye on at gRPC is how is the project evolving, growing over time. And it's been over 11 years now of gRPC, and we just continue to grow every day. And so want to thank all of you for making that possible, all the different bug requests, pull requests, your engagement with gRPC and making us continue to be super relevant and continue to be a really, really great framework for you to use. These are some of the details of what we see in gRPC. It's super impressive. Every week on Maven Central, 7.1 million downloads of the Java library. 24 million weekly downloads in Python, the number 72 library in all of Python, so super impressive, and 13 weekly downloads on NPM. And so a lot of folks out there using Node as well. And so we love seeing these numbers and continue to grow. And what we're gonna do today is tell you about a bunch of new features that we've been adding recently. And so if you haven't tried them out, check them out, and this is a great place to see what we're doing and what we're working on. One of the feedbacks that we got at KubeCon was that many of our developers found our documentation was difficult to use, and we didn't really stand up to other libraries. And this is something that we put a ton of effort into fixing, and hopefully have made it at par with a lot of the other libraries that you're using. And you can see we created 4 new large user guides that were missing, 4 new code examples, and invested heavily in videos. So we've recently put 39 new videos up on our YouTube channel. And hopefully those resources are helpful for all of you and make it easier for you to use gRPC. One thing I want to do before I continue is I do want to let everyone know we would love any contributions that you have, either through pull request or just opening bugs and letting us know. If you are having any issues, we'd love to know about it and we'd love to help you. And so definitely feel free to engage with us on gRPC and in those ways or others. Another great way to engage with the gRPC team is an annual conference that we run. And so we run gRPC Conf, and this is a picture from 2 years ago when we celebrated 10 years of gRPC. So this was 2 years ago. And we recently had our 11-year anniversary at gRPC Conf. And as a matter of fact, next week, our next speaker, John and I, will be going to India, where we'll do our first ever gRPC Conf India. And so absolutely, we're probably not going to see many of you in India next week, but all the content from that will be up on YouTube. You can go see stuff that we haven't had, new talks that we haven't done before. So it's a great opportunity to do that. And so with that, I will hand it off to John.
Great. Good morning, everybody. I'm John Feig. I'm one of the engineering managers on the gRPC team at Google. So it's been more than 10 years since the public release of gRPC in 2015, as Kevin just mentioned. In that time, gRPC has gained rapid adoption across various industries. It's high performance and support of many languages has made it the go-to solution for building efficient and scalable communication systems for modern distributed environments. Cisco began integrating with gRPC roughly a year after we released it. Netflix contributed to it and used it for its backend communications since 2018. Spotify adopted it in 2019, followed by Reddit, LinkedIn, and others. In fact, at KubeCon last year, LinkedIn talked about how they migrated 50,000 production endpoints from their internal framework to gRPC. It was phenomenal to hear that. It's so incredibly rewarding to see how our solution is being embraced by our users and making positive impact across various industries and applications. So what makes gRPC so successful? gRPC has proven to be an exceptional fit for cloud-native architectures. It's designed to enable efficient communication between services using protocol buffers to reduce message size and HTTP2 for network efficiency and real-time communications. This makes it ideal for microservices that need to exchange large amounts of data. Its language-agnostic nature makes it easy to deploy on various platforms and infrastructure. It also allows developers like you to build and deploy services in your preferred programming language. This portability is crucial in cloud-native environments where it is common to build microservices in different languages. Last but not least, gRPC enables an architectural pattern for microservices, enabling teams to break down complex problems into small, well-encapsulated services. This enhances developer velocity in large organizations and allows smaller teams to work on different components in parallel, accelerating the overall development process. In addition, gRPC provides features like load balancing and retries to improve fault tolerance and ensure application reliability in distributed systems. We use gRPC heavily inside Google. etcd, Containerd, Kubernetes, and many other Google Cloud projects use it for their internal communications. gRPC has become the popular choice for building modern, scalable, and efficient applications in cloud-native environments. Over the past few years, we've committed to making cloud-native adoption easy so you can scale your services quickly. Proxyless gRPC Service Mesh streamlines the development process, eliminating operational overhead associated with managing and maintaining sidecar proxies. This approach not only reduces complexity, but also improves resource efficiency, making it particularly appealing for large-scale cloud-native environments. gRPC comes with many features which allow you to bring service mesh capabilities to your applications easily. AI and ML have, of course, been quite popular over the last few years, and gRPC is revolutionizing the way that AI and ML models communicate and operate. Its inherent efficiency and speed and robust support for real-time data streaming establish it as a key building block to train large models that we have today and to serve inference requests quickly. The efficient data ingestion and processing facilitated by gRPC significantly accelerates the model development lifecycle. Training large-scale machine learning models involves handling and processing enormous data sets. gRPC's efficient data serialization, powered by protocol buffers, combined with its ability to handle large payloads, make it a robust and reliable solution for streaming vast amounts of data directly into training pipelines. Thanks to its low latency and high throughput, gRPC is efficient at handling inference requests. Prominent machine learning frameworks such as TensorFlow utilize gRPC to manage and process vast amounts of inference requests. NVIDIA's Dynamo Triton framework handles the deployment of servicing AI models use gRPC as their transport. gRPC ensures that real-time applications receive predictions with minimal delay. We're doing a lot of work in the AI/ML space. Over the years, our developer community has raised a number of challenges to us in building out their cloud architectures. There are three main pillars in our approach to providing solutions to those challenges. The first should be no surprise if you've been to any talk on gRPC in the past 5 years: service mesh. In 2019, we decided to set out on the long journey of creating a service mesh without sidecar proxies. We did our GA launch in 2020 and haven't looked back since. New feature requests have just kept coming on since then. And that trend did not stop this year. Just about every feature I'm going to mention today is related to Service Mesh in one way or another. Next is observability. gRPC went all in on OpenTelemetry a couple of years ago, making it easy for gRPC users to collect and export logs, metrics, and traces. That journey is not complete yet, and so you'll see a number of improvements we're making in the OpenTelemetry space. Finally, modernization. The world moves fast, and it'll leave you behind if you don't keep up with it. This is true for every language that we support. And for new languages rising in popularity, some of our most exciting projects come from this modernization pillar. So with these 3 pillars in mind, let's take a look at some of the upcoming features. We'll kick things off with a pair of killer proxyless server mesh features, extproc and extauthz. extproc is about modifying incoming requests and outgoing responses on a server, similar to gRPC interceptors, while extauthz is about determining whether an incoming request is authorized. Both of these features use an interesting plugin mechanism. While interceptors need to be compiled directly into your server, both of these features work based on gRPC callout model, where the server calls out to a pre-configured gRPC server in order to fill that feature's functionality. So for extproc, request and response modification can be performed by a separate gRPC server, possibly co-located with the server or possibly centralized, rather than compiling in an extension. If you're a platform team, this is a dream come true. The power of gRPC interceptors will now be available to you to enforce across your entire system. All you'll need to deploy an extproc server and configure your service mesh to point at it. The same functionality will be available client-side as well. That is, the client will be configurable to modify callout to an extproc server based on its requests and responses. extauthz works similarly. Each incoming request will result in an outgoing request from the application server to a pre-configured gRPC server, which will answer the question, is this sender authorized to make this request? This new plugin model will offer you new levels of flexibility in building your systems. The feature is still in the design phase, so be on the lookout for a gRFC laying out the details later this year. Next, serverless integrations. Service mesh operators generally don't just run Kubernetes. Whether they like it or not, feature teams in their organization often run workloads on various server platforms as well, such as Google Cloud Run. Unfortunately, there hasn't been great interoperability between the 2 types of platforms for service mesh. For gRPC proxyless service mesh in particular, we've seen good support for Cloud Run to GKE. In fact, Kelsey Hightower demoed exactly this when proxyless was first introduced. But the other direction, Kubernetes to serverless, hasn't worked out nearly as well. So, with Google Cloud Run in mind, we designed and implemented a handful of features that make this a first-class experience. First, we've added XDS host rewriting that enables the use of vanity URLs in XDS targets, something very common on serverless platforms. Next, we've added JWT token-based authorization for outgoing service mesh-mediated RPCs. And finally, MTLS auth based on SPIFFE identities. Putting all these features together, the integration between serverless and proxy service mesh is now truly first class. Now I'm going to hand it off to Israel from Broadcom.
Hi, I'm Israel. I'm a software architect at Broadcom. We use gRPC extensively as a fundamental communication pillar across all our modern microservices. So next feature is HTTP Connect with the XDS integrations. HTTP Connect is actually a special HTTP verb that allows setting up a TCP tunnel through the HTTP proxy. We can run different protocols over that, but in the conversation here, gRPC is the most relevant, obviously, that can be tunneled over the HTTP connection. And it's useful in 2 main ways. One is the forward proxies, so you can enable egress from a network environment that otherwise disallows egress. And for reverse proxies, when you enable ingress into a network where ingress is generally disabled. So example would be you can use HTTP Connect with a reverse proxy to individually contact servers deployed in public cloud from an on-prem environment when those servers are otherwise not accessible from the public internet. gRPC has had support for tunneling with HTTP Connect through proxies since 2017. The functionality was defined in the very first gRFC, the A1. Now we're making this functionality much easier to configure. Previously, it was only configured manually in a per language way. Now it's being extended to integrate with XDS. So XDS would send configuration based on destination service or server where HTTP Connect is needed. Users of early versions of this feature already take advantage of it to create a single service mesh that spans across their on-prem and cloud environments. Next is support for multiple SPIFFE trust domains. As a brief intro, SPIFFE is a system for assigning cryptographic identities to individual workloads and then being able to verify those identities. The workloads could be pretty much anything, virtual machines, Kubernetes pods, or anything else. These cryptographic identities can then be used to establish MTLS connection between the workloads. And as you might know, setting up MTLS manually is a huge hassle. gRPC had supported configuring SPIFFE-based MTLS via XDS since 2021, but only via certificate authority files. We're now adding support for SPIFFE trust bundles. This will allow you to take advantage of multiple SPIFFE trust domains. When is it useful? This is useful actually in a bunch of different scenarios, separate, and one of them would be, for example, a separate root of trust for development, staging, or production environments. Useful to ensure that less secure environments, like staging, cannot accidentally access production. Each product area, another useful case is each product area within your company might handle its own identity management. In this case, clients will still be able to interact with workloads within the same trust domain or across trust domains. And we can expect this to land in C++, Go, and Java later this year. Like we mentioned in the beginning, service mesh and observability are two of our strongest pillars in gRPC, and the intersection of these two spaces is just as hot. We're adding OpenTelemetry metrics for weighted round-robin load balancing policy, the peak first load balancing policy, and for XDX client. This is the component that gRPC library internally uses to connect to the XDS control plane. In addition to these 12 new metrics, we're adding cross-cutting labels to indicate the XDS locality associated with the metric. This would roughly correspond to a cloud zone. Originally, all gRPC OTel metrics operated on a per-call basis. We recently introduced a framework for non-per-call metrics. For example, the XDS client, which is used across multiple calls and even multiple channels. The non-per-call metric framework enriches the observability available to users of gRPC in a proxyless service mesh case. Together, these features will make running a service mesh with gRPC easier and more reliable than ever. I'll pass the microphone to Ivy.
Yeah, thank you, Cyril. Hey everyone, my name is Ivy. I am a gRPC maintainer and I work on gRPC Java. Today I will spend some time to talk about a few new features around the load balancing area. So the first feature is custom backend metrics. This feature is a mechanism for you to inject metrics from the server side, and it will push to the to the client side, specifically useful for load balancing. We are following the Open Request Custom Aggregation, ORCA specification, and we support two mechanisms to report metrics. One is through each RPC's metadata, training metadata, when it finishes. So basically, we transmit the metrics through the channels that we are sending our RPCs. And the second mechanism is that we periodically push down the metrics from the server to the client. This feature, the custom backend metrics, is available now in production, and feel free to use it. If you want to learn more details, there is a short link here below to take you to a few examples and documentations supported in multiple languages. The next feature is about WRR load balancing policy. It can be used together with the backend custom metrics. So to configure it is really straightforward. If you set up your CSM, if this is in CSS environment, you will just set up the custom policy to point it to WRR and then supply a few parameters to configure the load balancing. You can also add a few fine-tuning parameters. If you are not using it in CSM or TD environments, you can still use it in your library. So this code snippet shows that, for example, in Go language, you will configure the load balancing service config in JSON format when you are dialing your RPCs in your application. So once you configure LB policy, the last step is to start setting up the backend metrics from the server side. Here is the formula that gRPC will use internally to calculate each backend's weights based on these metrics, for example, the QPS, the CPU utilizations, and the error rates. This is an example showing on the screen about using OOB reporting at the gRPC Go server. So you will set up a matrix recorder, and you give it a few options. For example, you want it to run out of band, and then periodically you refresh matrix every minute. You register it into your server side, and then you can start sending the metrics, for example, the CPU and the QPS. This is all you need to set up the WR for gRPC. And again, more details, you can link to this short link below for more details. And now I will hand over back to John.
Great, thank you, Ivy. Next up, we have some very interesting developments in the AI space. 2 protocols to enrich AI models with external data and capabilities have absolutely exploded in popularity over the past year. MCP, the Model Context Protocol, and A2A, the Agent-to-Agent Protocol. MCP gives developers the ability to enrich LLMs with abilities of any tool that you can export via an MCP server. You can imagine search, file access, or any other traditional software application. The second protocol, A2A, gives long-lived AI agents the ability to collaborate with one another in a structured non-English language. A2A was built from early on with gRPC support, and the protocol is fully defined in terms of protobuf. The MCP HTTP transport based on JSON RPC was designed in a way that makes it difficult to support in a typically horizontally scaled load-balanced development or deployment. Since then, we've gotten many requests to enable MCP over gRPC with all of its rich features. In August, we made the announcement that we'd be working with the authors of MCP to add support for gRPC. We're now in the process of publishing an experimental fork of the MCP Python SDK with gRPC transport support as a proof of concept. And we're continuing to work with Anthropic to add a pluggable transport API to their SDKs that will allow us to distribute the gRPC transport as a separate package that plugs into their SDK. Adding something like this, like a new transport to the official MCP specification SDK, will require a lot of community interest and usage. The experimental fork can provide that signal to the community and help determine next steps. gRPC has established itself as a key component in the AI space. I'm looking forward to seeing what applications will come next. Okay, back to Richard.
All right. So my name's Richard. I'm a maintainer on the gRPC project, and I get to do a fun slide. So last but not least, we have the newest entry in the family of officially supported gRPC languages, Rust. Rust has become incredibly popular over the past few years with its safety by default and zero-cost abstractions. And no language is complete without first-class gRPC support. So we're working to make sure that that support is there. We're building on top of the already very popular Tonic implementation, bringing it to parity with the other first-class languages like C++, Java, and Go. And that will mean a full XDS implementation so that you can use gRPC Rust in your proxyless service mesh deployments. We've been working directly with the author of Tonic to make sure that we deliver the best possible experience to both existing users of Tonic and new users of gRPC Rust. That work resulted in a preview back in August at gRPC Conf in Sunnyvale, and we expect more to be available very soon. Our gRPC Rust team did an in-depth talk on the new library at gRPCconf. So in case you weren't able to make it to that event, you can check out the video of that talk on YouTube. So that was our whirlwind tour of what's new in gRPC. Hopefully you found a few features in there that are interesting for you. As always, there are a bunch of ways to get involved in gRPC, either as a user or as a contributor. We have our grpc.io website, which Kevin mentioned has been recently expanded with pretty comprehensive documentation and guides on all of our features. There's never been a better time to get started with gRPC. There's a YouTube channel where we're also documenting with videos telling you all about these features. We've got meetups, we've got the mailing list if you have questions or you want to get involved in developing the project, and you can follow us on X. So with that, I think we'll move on to questions. And there's a mic in the center, so if you want to come up and get in a line, we want to make sure that we get those questions on YouTube, so it's not just the answer, people are guessing what the question is. Yeah, head on up to the mic.
One of the problems we have was the sharing of the proto files. So what ended up happening was that people would have the proto file in their project, and then people just copy and move to another project. I don't think that's the best way to do it. I don't know if there's anything that you guys have created or thinking about how to distribute those proto files in a more efficient way.
So there are a lot of ways that people address this problem. Copy pasting or like just copying files between repos is probably the worst possible one. You can get desyncs. I'm sure you're aware of that. The simplest possible thing you can do is a git submodule, assuming that you have multiple repos. If you're using a monorepo of any sort, this problem's immediately solved. Then there are systems like Bazel that give you sort of a virtual monorepo. So even though you have separate repositories physically, you have a build graph that spans those different repositories. And from the perspective of the build system, it makes it look like a monorepo. Okay, so two solutions there. Then there are schema registries as well that are available if you want to use those to sort of achieve a similar result with the build graph. But those are more tuned to gRPC and protobuf specifically. So the one out there that you'd probably use would be buff and the buff schema registry, BSR. Cool.
Hi. Lots of times the internal communication that's done with gRPC kind of mirrors the external communication that we want clients to talk with our service. And when we try to program an SDK for users to use the API, it's quite uncomfortable to use the generated gRPC code to actually view these classes and objects for users to actually understand what they're doing. And it usually forces us to write our schemas twice, once in gRPC and once in native Python or whatever the SDK is. And I was wondering if there's like some effort to make this simpler.
John, you want to take it?
Sure. Yeah, this is a question that comes up a lot. And so, like, I actually recently sort of built and ran a service on a different team at Google. I fully owned the server sort of design, architecture, implementation, and worked a lot with, we had like a server, and then we had a bunch of mobile clients. And so we had a proto file. And what we did was we just used protocol buffers. That was the object that we used throughout the service and on the mobile application. And what that does is, there's some efficiencies to be gained with the communication, but it also, there's a lot of nice things that protocol buffers offers. For example, null safety. So, if you forget to populate a required field, it won't let you build it. It'll fail right there. Or if there is a nullable field, it gives you nice ways to check and things like that. You do get the efficiencies of not needing to convert between the native object and protobuf and back and forth. There's also other things that you can do, other services that actually directly work with protocol buffers. And so, that would be, my personal recommendation is look at that and see if it's actually a viable path. You can actually eliminate quite a bit of code from your application if you're not constantly swapping back and forth. And that swapping back and forth is a source of errors. So at a startup I worked at years ago, We used protobuf, and that was specifically a place where we got null pointer exceptions, was converting like protobuf to plain old Java objects. So that, like, my personal recommendation would just be to consider, if you can, directly using protocol buffers in your application.